Hello, this is Eloisa with Math Leopard. Today I'm going to show how to derive the sum of a geometric series. To begin, we want to prove that the difference, 1 minus r to the nth power, is equivalent to the product of 1 minus r with the quantity 1 plus r plus plus r raised to the n minus first power. The easiest means by which to show this is through induction. Consider n equals to 2, that is, 1 minus r squared. Is this equivalent to the product of 1 minus r and 1 plus r raised to the 2 minus first power? Well, this simplifies to 1 minus r times the quantity 1 plus r, that is, the difference of squares. Hence it is indeed equivalent to 1 minus r to the n, where n in this case was 2. Considering n equals to 3, that is 1 minus r cubed, is this equivalent to 1 minus r times the quantity 1 plus r raised to the 3 minus first power, or 1 minus r times the sum of 1r and r squared? Well, this by definition is the difference of cubes, so yes, it is indeed 1 minus r cubed. Check mark. Moving to n equals k, we can set 1 minus r to the kth power equal to 1 minus r times the quantity 1 plus r plus r raised to the k minus first power by assumption. But will this hold true in the k plus first case? Is 1 minus r raised to the kth plus first power equal to 1 minus r times the quantity 1 plus r plus r raised to the k minus first plus r raised to the k? Well, let's regroup the terms inside the second factor, such that the quantity 1 plus r plus r raised to the k minus first power is in one grouping, and the plus r raised to the kth power is in the second. I can now distribute 1 minus r to the first group, that is 1 plus r plus r raised to the k minus first power, to which we then add 1 minus r distributed to the second group, i.e. r raised to the k. The first term can be rewritten as 1 minus r to the k by induction, as it is equivalent to our assumption for n equals k. Distributing and combining like terms leaves us with 1 minus r raised to the kth plus first power, which is an equality. Hence, 1 minus r to the n is indeed equal to 1 minus r times the quantity 1 plus r plus r raised to the n minus second plus r raised to the n minus first power. Dividing both sides of this equality by the factor 1 minus r gives us that the quotient 1 minus r to the n over 1 minus r is equivalent to 1 plus r plus r raised to the n minus second plus r raised to the n minus first, which can be written in summation notation as the sum sigma as index I counts from 0 to n minus 1 of r raised to the index I. Now consider a ratio r raised to the nth power where r is strictly less than 1 in absolute value. For example, 1/2 to the nth power. The corresponding sequence a sub n of 1/2 to the nth power is given by 1, 1/2, 1/4, 1/8, 1/16, 1/32, 1/64, etc. That is, the limit as n becomes infinite of the sequence a sub n is equals to 0. Therefore it should be clear that subsequent powers of ratios strictly less than 1 have a limit of 0. That is, the limit as n becomes infinite of r to the n is equals to 0 for all r strictly less than 1 in absolute value. Now let's consider the corresponding series. That is, the sum as index n counts from 0 and increases without bound of r raised to the index n. This is really the limit as n becomes infinite of the finite sum as index I counts from 0 to n minus 1 of r raised to the I. However, we just showed that this finite sum was equivalent to the ratio of 1 minus r to the n over 1 minus r. Now, given that this is a continuous function on its domain, we can push the limit inside of the function to affect only the term containing n, that is r raised to the nth power in the numerator. As we showed, this limit is 0 for all ratios r strictly less than 1. Hence the sum of the series simplifies to 1 over 1 minus r. Therefore, the sum as index n counts from 0 towards the infinite of r to the nth power is equals to 1 over 1 minus r. We now take this equation and multiply through by the constant a. What results is that the sum as index n counts from 0 to the infinite of a times r to the n, that is a geometric series, is equivalent to a over 1 minus r. And thus it is shown. I hope this video helped to clarify the why behind the sum of the geometric series. I'll be creating more videos soon, so please subscribe to be updated when they're available. Thanks for playing, and I'll see you next time.